And I thank you and your team for the opportunity to be here, well, for the school, at least part of the school, and this morning. I've been working in this area probably, scary, it's almost 20 years now, machine learning specifically, but I think even from the very beginning I was interested in lifelong learning, or at least the ability to acquire models from experience and then store those away and use them as a source of knowledge when you're learning something yet new again. It seems to be like the right thing to do. So as you can see here, this is not just my work. There's also a number of colleagues and master's students and a PhD student or two in there. So this is my fundamental position. Hopefully it agrees with most of you around the room here today, that it's time to move on to doing lifelong learning, bigger AI types of things. And specifically in regard to learning, the motivation, rationale, is that there's now quite a large and healthy body of related work in this area of doing lifelong learning. And we've got computing systems, even on our own desks here today, they're capable of doing things that can push the envelope a little bit in some of these areas. And then with groups of computers, some very large ones, which I'll talk about later, they've done some pretty incredible things just in the last year. And there's clearly challenges not only to understandings in AI, but also to brain sciences, healthcare, things like these even potentially over time. Learning for young children is another area that, and deficits in those sort of spaces, I think that can be acquired from this over time. So eventually I'm going to be showing you an example of how we can use learning of a fairly complex problem, that of morphing a person's face. So I'm going to eventually show you images of a passport photo like this fellow with his ball cap on backwards there, and a neutral state, and then the ability to transform that to an angry, happy, sad face. So the idea was, this is a fun exercise to be able to create a model for doing this, and then present it with an image of someone it's never seen before and see if we can create a picture of them smiling, sad, happy, that type of thing. And using transfer rather to do that was one of the goals. So we'll come back to that, but that's the type of interesting things we're interested in. Clearly there's applications for this in robotics, you know, Google, I'm sure might be interested in these types of things, the military, et cetera. I do want to mention the fact that there is an interesting new symposium that just was proposed at AAAI, and it's coming up at Stanford University as part of their AAAI Spring Symposium, and I'm working on this symposium with Eric Eaton, and so even in that context, we're starting to see more interest in this space. So this is the broad outline of what I'm going to cover over about the next hour, really. So I'm going to eat into about, as Kristen mentioned, about 15 minutes into the next half to finish up, mostly talking about futures and where things are headed and new ideas. Before that, I'm going to talk just a little more generally about machine learning. And I've gotten a pretty good sense over the last couple of days where many of you are at, but I'll take a poll in just a moment here. Once we all feel relatively comfortable in some of the basic areas, and that of inductive bias, inductive transfer too, it's an important area to cover. We're going to get into machine lifelong learning and some related work that some of you have seen or read about. And then specifically context-sensitive multiple task learning, which is something I've been working on since about 2005, and some of the interesting things that it brings and problems that it solves. And then the last 15 minutes, we'll look at challenges and benefits of futures and that sort of thing. Okay, now, first of all, how many people fundamentally understand what I'm talking about when I say machine learning? Perhaps a better question is, how many people have actually built models using machine learning technology? Put your hands up real high. Okay, so there is maybe 4 or 5 who have not. So I'm just, for those 4 or 5, I'm going to give them a very quick kind of overview of what this is about. We can say from a mathematical perspective, and I realize this is very much the CS traditional AI type of bent here as an opening, but we can talk about this as developing general models from examples, experiences of the world that your robot or agent or your data mining piece of software may have. And it's like curve fitting And if you like, and I think I can bring this up. So one of the puzzles for those people who are familiar with machine learning is that you try to guess what the x and y axis here are. So this is a phenomena, a relationship between variables, two variables, and if we want to fit a general model to that, essentially a curve to it so that we can do prediction, we're faced with one significant challenge, and that is, what's the general shape, I'll call it, of the underlying model that best fits it? So this is just Excel I'm using, but if you use this and go to add a trend line here, so there's one of the simplest models we can put to it. It's a line. Now there's a bias that comes with that. The assumption here is that the best model to fit that set of data points is a line. So all we're going to be able to do with it is turn it this way, translate it up and down, but that's all our free parameters are able to do. Now how many people like that model? Is that a good one? Happy we can all go home then. Maybe, how about this one? Is that better? Oh, that one maybe feels a little better. There's clearly some variation, which you might expect from any kind of empirical study of things. Anybody willing to guess now what this data is about? Well, actually, the y-axis is income in thousands of dollars, and the x-axis is age. The data's from. So the message here, and we can make this even more complex. We can kind of increase the power and that sort of thing to it. But all those are choices that are made. So one of the big unknown factors here in terms of learning as we advance in this area is how we chose this strategy, if you like, heuristic, the bias, the model from one to the other. Because until you have that, it's really difficult to fit, even if you fit the parameters to it well, you could end up with something as simple as this linear model, and it just doesn't do very well. So that generally is referred to as of inductive bias, or the bias around choosing the model to which the parameters will fit. So it does require some type of heuristic or bias. How many people here use biases? Yeah, that's right. Some of them are pretty bad, too. North America in particular, we have a lot of bad biases. I don't know if you're into hockey, but some people really love the Toronto Maple Leafs. They're terrible. But they just keep going to those games. How do you choose which to use? Well, here's a fun little thing. How many people, when they look at this, what do they see? What's that read up in the block? Well, let me give you a knowledge background, which we can say is inductive bias. Okay? See the transfer happening there? Oh, but wait a minute. Let me give you some more background knowledge. Now what is it? Statistically, what is it? First read or first? I'm not sure. So background and bias makes a big difference. It fills in the gaps. And in fact, we know that there's no sense in doing machine learning unless you actually come with the bias. Because without that, or in the absence of all of the examples of the phenomena, you really can't build any kind of model for doing prediction. You have to have bias, or it doesn't work. So it requires both prior knowledge, background, and I think this is what's exciting about this and the fit with AGI in general is that this view of machine learning provides the method by which we can build common understanding, common background knowledge in order which to do reasoning, planning, and other future learning. But it's not only the acquisition, it turns out that there's another problem too, and that is how do we select the most related knowledge when it's time to actually make the determination as to what the bias should be for this particular problem. And again, as humans, we seem to do this very, very well. And oftentimes we identify it with expertise. If you ever worked on a software problem as an undergraduate student, and then an upperclassman walks in and you ask for some help and they kind of go through your code, oh, your problem's there. And you're like, how do you know that, right? But it's the bias that they bring to the problem. The knowledge of the language, having been there before, that's how they zero in, identify the problem area, and find a solution. And we tend to say they're brilliant, they're smart. Well, yeah, they are, but it's for a reason. This is just that there has been some work on this that identifies some areas. The ones we're going to focus in terms of bias is knowledge of these last two, knowledge of the task domain and analogy with previously learned tasks. But we all know about this one because we've all been in classrooms. Just think about when you go to study for your exams, what bias do you bring in terms of the material that you focus on in studying for the exams? This is the thing that the professor liked the most, the thing he talked about the most, he was most animated about, has written papers about things like this. So it sounds to me like most of you have a pretty good sense of this. I just want to bring up the fact that there are three different broad classes of machine learning. That of, first of all, supervised learning, which tends to be the most heard about technique, where you have a set of examples, X and some target value, a set Y. For example, you're trying to diagnose disease, like diabetes. So you have a series of input parameters, the person's age, gender, various simple clinical parameters, their eating habits, and then an output value Y for each of those patients, and you put them into a pool of data, you give them to your machine learning system. The challenge is to develop a model for predicting disease in a person, in a future individual. Now, unsupervised learning has to do more with taking examples without a supervisory signal and clustering them into categories. So this is often was originally done in many areas like marketing and business. If you've ever heard the term yuppie, which is young, upwardly mobile or something like that, it's a result of a clustering activity, actually in marketing. And there's probably an acronym for the old fogies with lots of money or something like this, but these are categories that got created by looking at the data and grouping them together. And then you can put kind of a target label on them if you like and use it in the future. But this is useful, particularly now with the internet and the plethora of information that exists through Google, for example, and Twitter and things like this, to be able to take data for which we don't have labels, like images without labels, text for which we don't really know its title, and to be able to automatically cluster that into areas. So there's a lot of work on the use of unsupervised learning now in terms of automated summarization of text, automated titling, classification, because it's absolutely gross how quickly the web grows, how many new documents are put up every day. So if you're a librarian wanting to index all this, you have to have some kind of tools like this. Reinforcement learning, similar to supervised learning, only, well, this is a really gross, I guess, simplification of it, but reinforcement learning has no signal, supervisory signal with every example. It's like playing a game of chess and then winning or losing at the end, and then you have to assign credit backwards to every one of your chess moves that you made. And for much of what we do as humans, this probably comes closer to a lot of the real learning that we undertake. Turns out the mixture of these things is likely the best route. So this is your traditional framework in a machine learning 101 class. This is the one you're usually presented with. You have some instance space X of examples of input variables. Hopefully there's a phenomena, a real phenomena that has some statistical validity or causal validity. For example, X is your input parameters for your patients. F of X or Y is the diagnosis of disease, like diabetes. And we steal from that instance space a set of training examples because we can't get them all. We can only get some of them. That's because, one, it's costly, and two, it takes time to get them. Those are the realities. So think of your robot or your agent on the web moving around, same type of problem. They can only gather up so many examples in time frame or at a particular cost of energy and these sorts of things. We get those examples, we push them through a system that is able to create an inference set of rules or equations. That's an inductive learning system. We generate from it a predictor or a classifier. So a classifier is particularly focused on identifying whether the subject or the patient has disease or does not have disease. Or alternatively, it could be a categorical type of thing where it's saying it has disease, diabetes, or Alzheimer's, or heart disease. It could be that type of thing. If it's a prediction, then maybe it's predicting predicting temperature or the amount of dollars that will be sold or something like this. But let's focus on classifiers. In particular, usually machine learning reduces itself down to talking about concept learning. You're learning whether they have disease or not, is it a cat or not, is it human or not, that sort of thing. So in that case, we're looking to generate from this learning system some hypothesis or model, H, which will take the original input for a new example, X, and produce the appropriate output. That's the goal of machine learning. Now, our problem is, just as an example, again, for those people who haven't experienced machine learning, we want to classify each of you in this room based on your typing habits. And this is one I worked on actually with students, and it's a fun one to do in a machine learning class. Work it right through actually as you conduct the class. So you got your keyboard typing, so I don't know if anybody's ever done this, but you can actually do it pretty well with an N of up to about 12 or 15, and then people's typing habits start across that larger population, lose their uniqueness by and large. So this is our problem, and our approach generally to machine learning is we acquire lots of typing examples of each individual. We then extract the features that we want from that, which are typically inter-character times. Turns out when you're typing, you're not actually holding down one key at a time. I don't know if you know that or not. Typically, you're holding down 2 to 3 keys at a time. So how many keys are down simultaneously in the order that they're in? Lots of interesting things like that. Transform that representation as you need it, and then use an algorithm to fit the data to a model. You get all those issues of what bias should I use, that's all there. So this is representation in search, which is, generally speaking, the problem of AI and computer science. And then we test the model on independent set of examples from that same pool of data from the typers to see how well it did. So just to kind of characterize and give you a sense of what's going on in these systems, if you do a simple logistic regression, now in this case, we've got 2 different typers. So this is person A and person B. And a logistic regression, you can see that goes something like this, where it creates essentially a signal waveform, and at the halfway point of that, we can kind of characterize that it classifies the typing generally of person A as being. So hopefully in the future then, the person's typing speed, if we're just looking at one input feature, if it falls in this area, then we can identify it as being typing A. They're a little more quick, they're a little quicker, and they make fewer mistakes. Whereas person B types a little slower, tends to make a few more mistakes. That's basically what this is saying. Now, that, obviously there's some errors in this. You see the A's and the B's, that's where the model is erring. It's getting it wrong. If we want a little more sophisticated model, then we kind of turn up the notch, if you like, in terms of logistic regression to artificial neural networks, which are really just doing logistic regression after logistic regression. And its model starts to look a little more like this. It starts off as like a linear classifier, logistic regression, and then through the use of these hidden variables. Now, graphical models are being referred to as latent variables. It's able to create much more complex surfaces, such as you've seen here, and to better kind of demarcate the A examples from the B examples. And but it's still not perfect. It's still making some mistakes. It's never going to be perfect in a noisy world. And then there are other algorithms, such as decision trees. These are usually in their simplest form, kind of characterized in this input space sort of graphical view here, is creating demarcation lines that are always orthogonal to the input feature axis. So what it does is it creates a tree where it may ask, well, how many mistakes? It considers mistakes as being the most important thing, and divides all the examples in 2 directions or 3 directions. Then it says, well, what's the next most important thing to branch on? And it will look at the typing speed again. And at the leaves of the trees, it then identifies it as being either typing of person A or person B. So that when a future case comes along of A typing, you can follow the various mistakes in typing speed through the tree, and it will identify that person as being A or B. So this is how it tends to carve up the input space, right? And again, there's all the things that we talked about before in all these. There's biases because you have to make choices as to various tuning parameters that will be exercised here in making those splits. Now, one of the problems with this, and this was something that I certainly appreciated early on, is that typically statisticians, when they're doing modeling, or machine learning, data mining people in particular, they build a model from the data that they have, they use it, and then they throw it away. And this just doesn't seem right in the big picture of AGI, for sure. So how can we do better than this? So enter this concept of machine lifelong learning. Now, I noticed that the symposium's coming up in the spring is being called Lifelong Machine Learning, so I can see there's going to be a little battle over the name here for this. But anyway, ML3 is what I've been calling it for some time. Considers methods of retaining and using learned knowledge to improve effectiveness and efficiency of future learning. So effectiveness and efficiency are both important factors here. How quickly you can learn a new model, because that's important for survival, and how effective, how accurate the model is. That's also important for survival as well, too, so you can go on to learn another day if you like. So in particular, interested in investigating situations and systems that must learn from impoverished sets of training data. So if you're a human or a robot or an agent moving through the web, at any point in time, incrementally, maybe you don't have that large a source of information to have access to, new experience of some new phenomena. And so you have to build good models from small numbers of examples, maybe only one example, as a matter of fact. You've got a diverse domain of related and potentially unrelated tasks. So this creates this cosmos of tasks which potentially could be harmful when you're learning something new. You have to negotiate your way in that. And that clearly has something to do with bias and selection of bias, which is the whole transfer problem. And we're also interested in systems that can practice over time. And this brings us back to AGI. If it's going to be a practical system, then it has to be capable of seeing examples of something you've already learned. And using those examples to benefit not only right at the moment, but also to benefit the prior task that was of that same phenomena, as well as potentially related tasks to that phenomena. And clearly there's lots of different applications of this. So we're back to this diagram, but now we're going to add to it. What we're interested in doing is, after we've built our classifier, specifically in this case, we want to retain some aspect of that. Even better, the psychological term for this is consolidation. So the concept is we don't just save away the new model representation or function, and those are two kind of dimensions, I guess, of what to save and how to do transfer, either representationally or functionally. But we need to integrate that information. It's not enough just to save it away. You need to integrate it, and that integration has everything to do with long-term efficiency and effectiveness, as it turns out, in a lifelong learning system and in an AGI type of agent. Once we have that knowledge, then we need methods by which we can index into it. How do we select the most related prior knowledge to affect a bias, right? To provide an inductive bias that's helpful, truly helpful. So if you have a collection of different things that you've learned, but only A, C and Z are really truly going to be helpful for learning this new function, Y, then how do you choose which of those to pick? And this is the knowledge transfer problem. And then generally this area has been referred to most recently as transfer learning. So historically, to look back just a little bit, quite a bit, Ryszard Michalski talked about constructive inductive learning. His model is very similar to what you saw in that last picture. And he made the important insight that perhaps the best thing to do, this harkens back to some of the comments that we were making yesterday, actually, is to not only look at how to use a representation to develop a model for a phenomena you're observing as an agent, but also how do you modify your representation to actually make it better at being able to create that model. Because if most of you have worked in this area now in computer science and math psychology, you know that if you transform a problem to the appropriate representation, the problem of search goes away almost completely. If you can view the problem, we have a human saying, now that I see the problem at this angle, the solution's simple. So again, if we can create a representation for the constraints that are of the environment in which our agent is in, that's most appropriate, then doing things like reasoning and learning starts to become easy. That's some of the comments yesterday we were talking about, what's the best kind of generative sort of, or seed to put in our agent. I think it's got something to do with that choice of representation to make things simpler. So he made that insight that perhaps the two should be going on at the same time, searching for models, but also searching for the appropriate representational space to build the models. Again, maybe perhaps this is what evolution figured out, how to do this. Utgoff, Polikoff, and Tom Mitchell, back in 1983, talked about the importance of bias. Some of the earlier material on bias, and the list of 5 different sources of bias came from Mitchell. And Utgoff made the important point that our learning systems really, what we should have been doing for the last 20 years, is been focusing on how do we choose the most effective inductive bias based on any information that we have. How do we choose the most likely model? Because once you have the most likely model, like the linear fit, the polynomial, then it's just a matter of fitting the data to that model, and it becomes relatively easy. Ray Solomoff did a lot of work in this, most particularly in incremental learning, and did a lot of work in terms of taking small functional components and being able to build them into more complex solutions and methods by which to grow those types of things, and as well as adding in more primitive concepts. Mitchell's student, actually, Sebastian Franz, many of you may know from, he just never seems to stop, this guy. He won the DARPA challenge, and most recently he's taught 150,000 students, right, in his AI. How many people took his AI course? That's amazing. Yeah, I sat in on parts of it as well. He did work actually in this area, and he came at it from the perspective that he got tired of putting his robots in a different room and them having to figure out the same things all over again. So he said there must be a way of transferring knowledge between rooms at least. So began work in this area. So worked on a thing in particular for his PhD thesis, explanation-based learning and transfer using particular techniques there. And used some of the first work actually using domain knowledge, previous tasks to affect learning. And 2 other people, Mark Ring, who is in the United States but spends a lot of time in Germany, I think, with Jurgensen. He has a system, his PhD was called CHILD, but still has continued to work in this area. And it builds more complicated hypotheses on top of already existing hypotheses developed. Similarly, in Montreal, Rivest and Tom Schultz, this was his PhD student, worked on cascade correlation neural networks, which actually build a model such as this one, and then can embed it within a network structure as it develops more complex models. So, for example, this might be the learning of, I'll keep it really simple here, the OR function. 2 inputs, and you have to learn the OR function, and this is the AND function, and up here you're learning the XOR function, which is clearly a combination of OR and AND, but it certainly can be more complex things like learning various diagnostic models and diseases where there's relationships between them. More recently, Jeff Hinton and Joshua Bengio in Canada, Jeff, of course, international recognition, and Joshua, too, with the work on deep learning architectures. I'm going to come back and talk and show you a little bit more about these later. But one of the most interesting developments, if you haven't seen NEL, which is the never-ending learning system, again, this is work with Tom Mitchell. Carlson is his student, I believe. And they've got a system now that's been running for 2 years that every day actually samples the internet, builds a psych-like repository of information, and then can reason with that information to actually then continue to learn new things. And they're actually using transfer in this approach. Let me see here. I think I'm going to come back to that. This is just a little bit of evidence that transfer learning and interest in this area of lifelong learning is growing. Unfortunately, not many are talking about a systems perspective. The machine learning people are very focused on, just taking a set of data, building models, and how can you do that better and better. It's hard to break out of that. That's why I'm excited to see the AAAI symposium. It's actually talking about machine lifelong learning. But in the transfer learning area, there's been a fair amount of work. The ICML conference last year, in particular, was a good one. This was just some slides, telling you about the increasing power of computing, and that it's now, feasible, I think, to really consider machine lifelong systems. In particular, IBM's Watson is a great example of taking already highly integrated or powerful computing systems, combining those in at least tens, if not hundreds, of computing systems, each with 8 16 cores on it, and then doing some very, very complicated learning and reasoning and combination of AI approaches, again, are being used here. So we have the technology, I guess. We can move out of kind of the, I'm always amazed at the work that people like Kolmogorov and these people did without computing systems, and we're at the point now where you can do a lot of empirical sort of studies and not rely as much on theory. Again, I'm going to come back to this and talk to it. What I'd like to do is to, before we stop, is just to cover basically the area I've been working on in terms of machine lifelong learning. And specifically, I've been working a lot with neural networks. We've done some work with support vector machines, decision trees, but very quickly they're difficult to work with. It seems that modeling systems that have hidden parameters, or in graphical models are called latent variables, are the best ones to use for doing this type of work. And I have a student who's just finishing up his master's, actually, work when I get back. He's doing his defense and seems to have verified this by taking same sets of data from several different domains and employing it against several different learning systems. It seems that's one of the key characteristics anyway, is that they have to have latent variables involved. So the inductive learning system, base learning system we're using here is just, we could just think of them as being your base simple backpropagation neural networks. We could apply other things, but it's easy to talk about them in this way, using this paradigm. And same thing in terms of if this is the short-term learning of something new, then you can think about the long-term memory, or the consolidated memory, as being an even larger artificial neural network, where the number of outputs continues to increase as we learn new things. So this is kind of like generation 1, and I'm going to tell you about generation 2 after the break, actually. So same problem, otherwise everything is good. The challenge is just how do we do this? So multiple task learning, first of all. Again, hopefully most of you have worked with neural networks. This is just your basic neural network. The difference is we have multiple tasks we're learning at the same time. And I think most of you would be able to see that if these 3 tasks are very closely related, like, for example, the OR, the AND function, the XOR function, then the features that are learned in these hidden layers hopefully are helpful to all 3 of those functions. And that by learning any 3 of them together, it turns out to be actually simpler and easier than learning each of them individually. And in fact, you can actually try that. You'll see that, in fact, XOR, which typically is one of your more challenging problems, is a small problem to learns very quickly when you learn AND and OR at the same time. But alternatively, it could be diabetes, heart disease, and high blood pressure or something like this, which are clearly related phenomena. You'll see similar sorts of effects. And the key here is this common shared feature layer of representation that takes the original input and re-represents it at a higher level, if you like, more at an abstract level, and then it steals those features away in different ways, but to some extent shared ways, with one task and the other. And the degree of relatedness between these, of course, is the atmosphere, if you like, on which you can have really positive transfer occur, or really terrible things happen potentially. So in other words, if bias is being provided, as it's stating right here, if it's occurring in this layer, if this is something new that you're learning, and you've got a bunch of things that are completely unrelated to it, then you may have a really terrible or negative bias, which has you come up with a model that doesn't work very well in the future. And we probably have all done that, I think, one way or another. And then corrected it, hopefully. So, how do we build a lifelong learning system on this? And this exists. Actually, you can download the software and try it. So let's start. We have to start somewhere in the diagram with the cycle of learning something new and then saving it away. So I'm going to say, let's say that we have this homunculus of consolidated domain knowledge, which is just a neural network with a bunch of outputs for a bunch of functions or tasks that we've learned. And we're interested in learning something new, some new function that a robot is moving around the room. He has to learn to find the power outlet, let's say. And so we create a separate little neural network, this output. And then the trick is we do something which I've termed as functional transfer. We take the input examples that we have, the example story that we have for the new phenomena. We not only train the new neural network on it, but we take those examples and we pass it through the network which we have saved away, creating the output values for each of those. Now, we've never actually been to those specific input sets for those problems potentially before. We've been in and around them. But as long as those models are relatively active for the input domain, for which we're receiving the new examples, then they should produce fairly accurate outputs for those old tasks that we've learned. So now what you have down here, I'll just run the animation again, is that you have the matching output values for each of the related tasks. So this is determining that the most related tasks for learning our new function F1 are tasks Y2, Y3, and Y5. Now, won't get into how do we choose those as the most related, but let's say that we have someone who can choose the most related task. Then transfer is done in this case by learning those 4 tasks together at the same time in this new short-term learning network. We could use all of them, I suppose, but it works best if you can pick the most related for this particular. Now, this problem of choosing the most related turns out to be the biggest problem, as a matter of fact. And if you can avoid, my current methodology is to avoid it. Not avoid the problem, but avoid having to make the choice. And that leads us to some of the most recent work. Okay, so we've developed a new model, and we've decided that it's accurate enough for saving in our long-term memory store. We do a very similar thing now. We add on a new output to our large consolidated network, and we actually consolidate it in using the same technology. We can produce now that we have a model for F1. So let's say we only had 25, 30 examples of that new task we wanted to learn. Moving to places in the room, finding the outlet, not finding the outlet, that sort of thing. And but since we have a model now with transfer, we can produce hundreds of examples of that, again, within the input space that we've been sampling. And so we've got lots of examples that we can generate now from this model. We can also generate lots of examples of our old stuff. So the issue of consolidation is one of rehearsing what we've learned here already in the past while integrating or learning anew the new task. So imagine then what you do is you start with the representation in the blue here dots, all those connection weights as they originally were before consolidation. But what you do in training this network for consolidation is you use lots of examples of the old tasks and lots of examples from the new tasks, all of which are generated from the models. They're not examples you've saved away. You have the ability to generate functional examples because you have the representation of the models. That's really key to this. If we have to save the examples away, then we've got this kind of huge memory problem we have to solve. Is that okay? Does everybody kind of see this? Because at the heart of this idea of what's referred to as task rehearsal that's going on here. We're rehearsing an old task while we're learning a new task. And it's through that rehearsal that we have a functional transfer of knowledge from one task to the other. Turns out that it's one way to solve the stability plasticity problem. Because up in here, that's what you have. You want to maintain those blue dots and their weights and everything like that. Or sorry, at least the ones at the top. Not necessarily these. These ones are shared, so they're going to necessarily have to change. So everything from here up is unique to each of these tasks. Everything from here down is shared across all of them. So if we're going to integrate this new task in, the weights here from here down are going to have to change. So the question is, how do you change the representation from here down that is shared across all of these, while at the same time maintaining the functionality of the prior knowledge? And what we're saying is the only way to do that is to rehearse what you've learned while you're learning something new. Does everybody get that? Because it's probably key. If there's one thing take home here, if you haven't seen this before, this is probably the big one. Because the stability plasticity problem is a huge, huge problem.
So you're not just using some function to merge the hidden layers. You're actually merging them while you're training again, retraining.
Because there was a lot of early work done on how can we take the current representation, kind of plug it in here, and then do better. As a matter of fact, you can take and build a whole new network for your homunculus, your consolidated domain knowledge here, set all the parameters to the initial random values, completely really learn on it. It turns out that that's probably the best way to go in terms of building effective models, accurate models. It's the worst way to go in terms of building them efficiently, because you're learning everything all over again, right? So there's a trade-off there. And we haven't solved that, by the way. That's an open problem, exactly how you do it. Gotten close to it, but yes?
And how's it doing with, in terms of complexity, if we are continually adding?
What happens, okay, here's the trade-off. Okay, if you go with sticking with the existing representation, integrating in the new, the existing representation stays pretty well, and you don't lose much on the accuracy of those models. And in some cases, the other neat thing is when you are adding in the new task, the accuracy of the old ones actually improve because they're related to one another. Okay? Oftentimes, though, the new task has a hard time getting integrated in. You can't move the weights in the system enough to bring it up to the level of accuracy of the original model that you learned down here. Now, I'm talking about maybe like a percentage point or half a percentage point. But the problem is when you learn things, a whole series of tasks, like 25 of them, one after the other, and look at what's happening to all the tasks in terms of their accuracy, you'll see that you lose a little bit on the new tasks as they're integrated in. If you completely eliminate the representation existing, right, go with a brand new kind of fresh set of weights and train everything new, what you tend to find is you lose a little bit on the prior knowledge, but the new task gets integrated quite nicely. So that little trade-off is occurring there.
We haven't figured out how to... Do you know of sort of a principled way to figure out maybe that you need to add hidden units there? If you have a new skill that's sufficiently different.
Yeah, okay, yeah. You're ahead of me. You're doing good, yeah. Yeah, sure. And there's another really interesting approach which reflects upon the human phenomena is that if you introduce noise into the system while you're learning, jitter, then you can actually sometimes build slightly better models in general, but it seems to help with consolidation.
Just a little bit, not too much.
Just a little bit, and that's the key, how much, and these little subtleties of it. Here's the other really interesting thing about this. This consolidation activity occurs and works best under and this Ryan Poirier found this out, works best. So if you've ever read a really interesting paper by Jay McClellan and Bruce McNaughton a long time ago about the was a cooperative or synergistic relationship between the hippocampus and the neocortex, because the hippocampus is essentially this. This is new learning, and the neocortex is this up here. It's generating a large set of engrams of prior learned things. Is that they found the very same things, or pretty close to it. You need a large amount of representation up here, which is the problem you just pointed out. Turns out you don't have to add more. If you've got a huge amount of representation, like millions of neurons, then you actually don't have to add more. A rich set of virtual examples for all the things that you want to consolidate. Really small, slow, interleave learning. And it seems to be the case in mammals that this type of consolidation occurs during REM sleep, if you're familiar with rapid eye movement sleep, you know, in that deep dreaming sort of state. And that you need to prevent the growth of, you need to prevent the generation of what's mathematically known as local minima that you can't get out of. You need to be able to keep the magnitudes, in the case of this model, the weights relatively low and yet represent accurately the models, because only in that way can you then bump them out of their position to add new things in the future. So those are the kind of practical problems that I'm interested in solving in terms of how to do consolidation and that type of thing. So anyway, we've applied this to not just domains of tasks, transfer from like 6 tasks to a 7th task, but we've actually, you know, learned the first thing, and then the second thing was transfer from the first, and then the third thing was transfer from the first 2, etc. And on several different domains. The first 2 are synthetic, so that we understood exactly what was going on between the relationship of the input and the output, and then probably 10 to 15 over the last 10, 12, 15 years, such as this is a heart disease problem, and these are different hospitals. So this is a case of where the different bars are showing the different modeling systems. So STL is just using the data from a particular hospital. MTL is with transfer from the other hospitals. And A to MTL is actually when you select a hospital which is most related to the new hospital, or hospitals that you're most related. That's the other interesting thing to consider with these when thinking about building an agent that's capable of lifelong learning. It has to be able to transfer knowledge not just from one thing in the past, but it really needs to transfer knowledge from multiple things, because oftentimes that's what we do. We put information together from different things that we've learned and come up with that ingenious solution for a new problem. Here's an example, fairly recent. Well, actually, this is a stream flow one. We've done one more recently with water management. Turns out to be a big problem in the world. So this is a challenge of, on this particular case, of stream flow rate, but we've done it for aquifer recharge. How quickly do wells recover after, you know, droughts and things like this? So this is actually my home province in Nova Scotia on the eastern seaboard, Canada. And we're interested here in predicting the flow rate of a stream given the weather 2 days ago, I think it is. So that's the challenge. And, you know, governments and people working in construction and planning can use these to try to model what the impact on water level will be given weather conditions. And so it turns out that if you need about 5 years worth of data in order to build good models for this, to predict the cubic meters flowing through the river at a fairly accurate rate. This is a great example of a practical example when we need to do transfer, because if you're now interested in a new point on the river or a completely different stream, then essentially what you have to do is go and monitor it for the next 5 years, and then I can build you a model. Well, you know, if you're the government planner, you're going to, well, what help is that? It doesn't help me. So it turns out that with transfer, if we're interested in the flow rate right here, if we have a year's worth of data and we transfer knowledge in from these other 3 rivers, we can build a model as good as 5 years from only 1 year's worth of data. Whereas the models from each of those used directly won't do it. As a matter of fact, this is a completely different river. Shubenacadie and STReP is actually a brook. It's about twice the width as Counter. And Annapolis River is probably about as wide as twice the width of this building, I guess. And so this graphic just shows you how the number of years that we have used for transfer affect the accuracy of the models. It also indicates that the best transfer is actually when you transfer data from, information from more than one model into the system. Now, this sets it up for break. I'm sorry, I'm over here. Limitations of this technology, however, it has a lot to do with the outputs. So spent a lot of time on this, and there's a lot of literature written on multiple task learning for transfer. The problems is that training examples, these examples have to match. So you've got some challenges here. You build up redundant representation. So F1 is actually the same as task FK here, but you don't know it as an agent. You just got a bunch of new examples, and you're building a new model for something you've already learned in the past. It might be better to kind of fit those two together. So it frustrates practicing a task, prevents a fluid kind of development of domain knowledge overall, and there's no natural way of associating examples with the particular task. Transfer is limited to this portion of the model. There's no sharing here at all. And lastly, you do have to have some method of determining what the most related tasks are when you're doing transfer. If you've got one new thing, 2 related, and 8 that are not related, then you could get really bad transfer. It would be better if you learned it without any transfer whatsoever. Can occur.